Okay, so in this problem, we're being asked to look at two different situations in which we're trying to find the impulse for. First of which is when a car is on ice and the brakes are fully applied after with the car having an initial velocity of 30 meters per second, the car will come to rest after 10 seconds. So it's asking us to find what the impulse was in that situation. The second of which is when the ABS is enabled, which causes the ABS system pulses the brake 15 times per second, making the car come to rest without skidding, which is better because you'll have more control after 12 seconds. So in this situation, both the mass, initial and final velocity, will be the same in both trials, but the time will be different. So before we start this, I just wanted to go over impulse one more time, impulse being that change in momentum. And in this situation, we will have a big change in momentum because we go all the way from high speed to no speed. So at that point, momentum will be zero since momentum is mass times velocity. So velocity is zero, momentum is zero. There's also a relationship you can see between momentum and force, which will rather impulse and force, which will be more pertinent in this situation, which will come into play later, since the problem also asks us to sketch the force versus time for the two cases, indicating the integral value in both cases. So let's go ahead and get started. So the impulse for trial 1, which with the brakes fully engaged, for this I just used the impulse equals mass times change in velocity, notably making the initial velocity negative 30, just to make my life easier because I like working with positives more, and to get that change in velocity, you have to do 0 minus. So 0 minus negative 30 gives us 30. So I went ahead and multiplied that 30 by 2,000, which is the mass, giving us 60,000 kilograms meters per second as our impulse. So the next thing we have to do is make that force versus time graph, which notably the integral of force is impulse. So integrals being in graphical form represented as the area under the curve, we can also use that to solve for this impulse and kind of have a more visual understanding of what's going on. So to solve for force, I just rearranged that underlined equation, giving us mass times change in velocity over change in time, which normally is F equals ma, but we can just plug in that 60,000 divided by 10, giving us 6,000 newtons for the force that the wheel is exerting in this situation to eventually lead the car to come to a stop after 10 seconds. So in graphical form, you can see that that line is a horizontal, and I shaded under that curve to show basically what the integral is. And I'm going to show in the next part how you can actually use the integral to solve numerically for this. But in this situation, I went ahead and showed how you can kind of solve geometrically once you understand that impulse is that area under the line in this situation. So you can just do the 6,000 times the 10 seconds, which gives us that original value we solved for of 60,000 kilograms meters per second. So in trial 2, the only things that have changed in this situation is that the time is now 12 seconds and also that the brakes are pulsing 15 times per second. So potentially you could do a really specific calculation on this to account for that 15 times per second, but that would just create so many data points. I'm just going to focus on the fact that the time is different, which will affect the force, which we'll see later on. But notably, it won't affect the impulse, as we end up with the exact same impulse as we did in the previous step, which makes sense because the change in velocity is the same and the mass stays the same. But you'll see where the two situations differ in the following step, in which we solve for force. So it's going to be the same setup as the previous part, but now we're dividing by 12 seconds, which gives us 5,000 newtons rather than 6,000 newtons. And once we apply that graphically, it looks similar, but now we have 5,000 newtons as our max force and 12 seconds as our time interval. And I went ahead and showed how that works out integral-wise, numerically. And you can see once we multiply those / just work through the integral, we get the same value of 60,000 kilograms meters per second for the impulse. So yeah, that is the problem.